Good afternoon, everyone, and welcome to Bruker Scientific Demo Lab here in Billerica, Massachusetts. We're glad you could be with us this afternoon. So today we will be showing you guys live um, how Moldy ToF can be used for the authentication of the botanical origin of dietary ingredients So just a few things to mention before we get started. You should have a few windows in front of you on a screen. So go to webinar windows, one with the presentation and also a few other ones for live cameras. I just want to let you know that you can adjust those windows depending on what's being presented and enlarge it, as well as resize the other windows accordingly. So you have a full view basically of what's being presented. Also, another thing, you should have one of the windows that says questions. So be sure to submit the questions as the presentation goes. Do not wait to actually submit the questions on the last minute. And we will have a few minutes at the end of the presentation and a live demonstration to answer any questions you might have. So make sure that you're typing them in as they come, and we'll go through them towards the end. So let's just a quick outline of how the next 45 minutes will go is we're going to look, I'm going to introduce you guys, or we'll have an introduction to the Moldy ToF process, how Moldy works in general, and explain basically, what are the things that go behind inside of the instrument as you're analyzing your samples. We will look at Bruker Moldy ToF instrument portfolio. So I'll give you guys a quick tour of our lab, just shows you guys some of the instruments, the Moldy ToF instruments we have in-house. Then after the tour, I will turn it over to Chris Krueger, who is from Complete Phytochemical Solutions, and he will give you guys a live demonstration on how to use Moldy ToF basically from start to end to authenticate the botanical origin of dietary ingredients, foods, and beverages. And then after that, he will be actually showing you guys the workflow live in action from his lab in Cambridge, Wisconsin. So he's doing it from his lab. And then after that, we will have Chris from Bruker Scientific also demonstrate how you can use FTNIR, Fourier transform near infrared spectroscopy, to detect adulterated foods as well. And he's also in his own lab in Wisconsin as well. So he will also go through that. Then we will conclude and then take some questions at the end. So first of all, Moldy ToF process. I have a video here that's going to give us more of an understanding of what goes on inside of the instrument as you're doing your moldy analysis. So the Moldy ToF process is a two-step process. So you have the moldy, which is basically the part or the phase that consists of matrix-assisted laser desorption ionization. So it's an ionization step that basically, after you insert the sample into the instrument, which I'm going to show you guys how easy that is also on the next few coming slides. The samples are bombarded by a laser, and the sample molecules vaporize in the vacuum while being ionized at the same time. And then after that, high voltage is applied on a target plate to accelerate any ionized sample molecules or particles that may be in the ion source. So that's the first step, the first phase, which is moldy. The second step is the time of flight mass spectrometry phase, in which the ions separate by mass. So basically what's happening here is you have all of the samples on a target plate experiencing exactly the same voltage, exactly the same accelerating voltage. And also you have the distance from the ion source to the detector, which is also constant. So the only thing here that's a variable that changes is the masses of the ions formed. And what happens in a linear mode, um, ions will hit the detector within nanoseconds. And since they have different masses, the lighter ones will be traveling faster, reaching the detector first, and then the heavier ions will be traveling slower, hitting the detector last. So that's what you see happening here. And flight time measurements are used to determine molar mass directly, basically depending on how much time it took the ions to go from the ion source to the detector. And that's converted into a mass spectrum that you can interpret and figure out what's going on in the sample. That's in a linear mode. In a reflector mode, the ions are diverted using reflector plates that you can see here on the top towards a secondary detector. And basically what this does, it does two things. First of all, the flight path is extended. It's a little bit longer, giving the ions more time to separate. And also the reflector plates help focus the ions onto the detector better. And both of those two variables will basically result in having higher resolution in your mass spectrum in a reflector mode than you would in a linear mode. So I'll let that play out so you guys can see what's going on. And this whole process is a very simple and fast process. Basically, for sample acquisition, usually takes just a few minutes. For per sample, usually not more than 30 seconds, and you're able to tell exactly what's going on in your sample. And here at Bruker, we have 3 levels of instrumentation. So instrument choice will depend on your application in a lab, what you're using it for, what you need it for. At the entry level, we have our benchtop microflex LRF, and this is a great option for simple moldy experiments, such as fast and easy QC of synthetic peptides, of oligonucleotides and other samples as well. And the nice thing about the Microflex LRF is it doesn't really take much space in your lab. You can put it on a benchtop. It's not very big. Comes with a resolution of 15,000, 60 hertz nitrogen laser. Can also function in both positive and negative ionization modes, and can go up to 300 kilodalton as far as how big of a sample you can analyze using a Microflex LRF. Next up in line, we have the AutoFlex Max, which actually Chris Krueger will be using today for the live demonstration in his lab. And this one is a workhorse, basically comes in different configurations and can do pretty much anything and everything that you can use MALDI as a technique for. And that includes MALDI imaging, that includes top-down sequencing, that includes MSMS experiments, which are very crucial for the elucidation of structures and also specific compound identification. This comes with a Smart Beam 2 laser that can actually go as fast as 2,000 hertz and can see up to 500,000 Dalton as far as molar mass goes in your sample. Next up in line, we have the UltraFlex Stream, which you can also see behind me here. And this one is our gold standard for polymer analysis, also for the analysis of very complex samples, complex mixtures, copolymers, or samples in very complex matrices. And this comes with a resolution of 40,000, a 2,000 hertz in smart beam 2 laser can also see up to 500,000 Dalton. And of course, higher resolution, the better information you can get from your sample. So if you have a very complex mixture or very complex sample, that comes in very handy. And this is something that you will not be able to increase later on as well. Lastly, on the top of the food chain, we have the Rapiflex, which comes in a vertical setup as well, just as the Autoflex, with a resolution of 50,000. And this is the best choice for imaging experiments. So if you run imaging experiments on a regular, this would be the best MALDI instrument to actually have. It comes with a 10 kilohertz laser, which means basically it can turn around your imaging experiments in a very short amount of time. A smart beam 3D laser, and can also go as high as 1 million Dalton in terms of molar mass. And it's also a ToF instrument which is capable of doing MSMS experiments. So I thought I would show you some of our sample targets before I turn it over. And this one here on the top left corner is a standard target. And these can hold up to 384 samples at a time. Next to it is the mini microflex target plate with up to 96 sample spots. And I have a few here as well. I'm going to show you how to insert it into the instrument in a few minutes. Next up is the anchor chip target plate, which can hold up to 1,000 samples at a time. And this is good if you want high sensitivity because it has the ability of concentrating your sample in a very small surface area to increase basically the signal that you get. And also really good for high throughput experiments. So if you're running a lot of samples at a time, this would be your sample target to actually go to. We also have a TLC adapter. So if you're doing TLC MALDI experiments, a imaging target as well that can fit in 2 ITO glass slides that are conductive for tissue imaging and other imaging experiments. And lastly, we have a direct target surface analysis that you can actually put any type of sample on, surface samples, of course, something that you would want to image. And you could just tape it on there using conductive double-sided carbon tape and be able to image the whole plate. Or even better, if you want to actually check what the chemical composition of that surface sample is at a certain area, you could also pinpoint to that and just analyze that area without any modification or using any types of solvents to change the chemical composition beforehand. So before we turn over to Chris Krueger, I want to show you. So I have one of the sample targets that I was working on that I prepared already. I'm going to show you how easy this is to insert it into the instrument. So basically, once you have prepared your samples and you're ready to get started, all you have to do is click, load and eject the plate that was in there. Open this inject window, insert it in, close the outlet, and then click loads to load your sample. And it takes a few minutes to get the pressures and everything in a vacuum inside of the iron source where it's supposed to be. And in about 30 seconds, you're ready to go and get started with your analysis. So at this time, I'm going to turn it over to Chris Krueger. Just a few words about Chris Krueger. He is the CEO of Complete Phytochemical Solutions, which is in Cambridge, Massachusetts, Cambridge, Wisconsin, sorry, like I mentioned earlier. And he has over 25 years of experience as a phytochemist, working on the development of mass spectrometry methods for the authentication of dietary ingredients, foods and beverages. He's also a member on several expert review panels, including AOAC, including the American Botanical Council, also the United States Pharmacopoeia. So without further ado, Chris, the floor is yours.
Thank you, Pierre. Can you hear me okay?
I can hear you clear, yes.
Very good. So let me start by sharing my screen here and PowerPoint presentation. Get this loaded up. Okay, can you see the, oh geez. I might be a phytochemist, but I'm not a AV specialist. Let me try one more time.
All right.
How's that work?
Still hasn't come on the screen.
Okay, let me try one more thing. How about now?
Yes.
Very good.
Yep.
Good. Thank you, Pierre, for the introduction here. This is the third webinar we've put together with Bruker and CPS, so I'm excited to share some new and exciting workflow demonstrations today. One of the things we're looking at here is the application of MALDI to identify oligomeric polyphenols. And I want to give a quick introduction to the role of CPS and what we do for the industry, food, beverage, dietary ingredients. We'll give a quick introduction to the anthocyanins and proanthocyanidins, two polyphenol groups that are important constituents in, again, foods, beverages, and ingredients. I'm going to talk a little bit about the ionization properties of polyphenols. And this can become challenging when we look at the data interpretation. So there's ways that we can manipulate the ionization event itself to make our data a little bit easier to interpret. We'll give a live demonstration from the receipt of the samples to the issuance of a COA, just to demonstrate how simple a workflow can be with the MALDI platform. And then we'll give a brief summary, and I will then turn it over to Chris Clark, the application scientist at Bruker. So just to get started, Complete Phytochemical Solutions, as I mentioned, does service the food, beverage, and dietary supplement market space. And one of the services we offer is what we refer to as polyphenol fingerprinting, or an approach to be able to characterize and identify unique components within a botanical, an extract, or a final finished product. And I think it's important to mention that the approach we take is what we refer to as an orthogonal approach. And that is one in which we are not dependent upon one single analytic instrument, platform, or method to support the identity or authenticity of a product, but rather we choose the most appropriate analytic platforms for the class of compounds that are characteristic of the original botanical material and what would be found in the ingredients that are submitted to us for analysis. We work across the spectrum of the marketplace, working with growers, processors, formulators, and retailers. So we may see an ingredient come through at multiple stages and support that identity and standardization testing throughout the entire workflow. So here's a couple examples. We have some blueberries, some grapeseed here on the left-hand side. These aren't blueberries, they're grapes. Grape seeds, we have cranberries, and we have pine bark. And these are all botanicals that are pretty easy to identify, except for this, which I thought was a blueberry. Apparently, I got to go back to my botanical identification class. But we've got visualization that helps us understand that, yes, these are really truly authentic items. This is a cranberry fruit. If we were to slice these fruits or seeds or bark and put them under a magnifying glass or a microscope, we can see the botanical structures. And again, this can help identify the botanical source. So these are part of a orthogonal approach to supporting the identity of foods, beverages, and ingredients. Where the challenge comes is when we take these botanicals, extract them, and purify specific components within the botanical. And what we see here are examples of a grapeseed extract, a cranberry extract, and a pine bark extract. And as you can see, we really do lose those botanical structures. And what we end up with is a very enriched product or ingredient in a class of compounds. And in these classes, we're working with proanthocyanins, or otherwise known as condensed tannins. But the difference between these is pretty hard to tell just by visualization. So our approach is to use MALDI-TOF mass spectrometry as a as a platform for being able to characterize the proanthocyanidins. And we have developed a method, an AOAC first action method, for the identification of A-type proanthocyanidins from cranberries. This same methodology that's described in this publication is what I'm going to demonstrate today, and it can be applied to a wider range of products beyond cranberry. Today we're going to look at grapeseed extract. Previously we've looked at pine bark extract. Anything that is in the world of complex oligomeric polyphenols is very well suited, and MALDI then is what we would refer to as a fit for purpose analytic. It's supporting the class of compounds that we truly want to use for the identity. So I'm going to give a very quick and brief introduction to two classes of compounds. One is an anthocyanin, and these are the compounds that provide the red colors, the blue colors, the purples in flowers, in fruits. And there are really a couple of unique aspects of this compound. And one is the most predominant, this positive charge that we refer to as a flavulinium ion. And this is important because in the MALDI environment, we're going to be analyzing in a reflectance positive mode. So this compound itself, or this class of compounds, will be detected as the actual mass of this compound because this positive charge is inherently a property of an anthocyanin. This compound can be substituted at various positions. You see the R1 and R2 position. So in addition to hydroxyl groups, this could be a hydrogen, it could be a methoxyl group. The R2 position is very commonly glycosylated. So we may have glucose, galactose, or arabinose substitutions. And these variations then can be detected very easily in the MALDI environment. The second class of compounds that we'll discuss, and where most of our effort today will be focused, is on a class referred to as proanthocyanidins. And this, again, the nomenclature here is difficult, but anthocyanins are the single monomeric compounds that inherently have the positive charge and provide pigmentation. The proanthocyanidins are polymeric in nature. So what we see here is a repeating catechin unit. Here's a monomer of catechin attached to a second monomeric unit, and then a third monomeric unit. Again, we can have substitutions in the degree of polymerization, hydroxyl substitutions, and the unique nature of the interflavan linkages. Again, MALDI is very well suited to be able to handle the structural heterogeneity that is present in proanthocyanidins. But unlike proanthocyanidins, or unlike anthocyanins, there are no positive charges that are an inherent part of this molecule. So for this molecule to be detected, it has to pick up an additional charge. So what could those charges be? As you saw in Pierre's demonstration, on the target here, we have a mixture of analytic and matrix that when impacted with a laser, desorb and ionize and travel down a flight tube. In nature, sodium, potassium, and hydrogen are abundant. So it is very typical for analytes to pick up a hydrogen, potassium, or sodium and fly as an adduct. In this event, what we have is the mass of the compound of interest plus the weight of the hydrogen, potassium, or sodium, and that is exactly what is being detected in the MALDI system. It's the mass of the molecule plus the ion adduct that is present. And just a reminder, here's the structure of an anthocyanin that can be flying as its own unique charge because it is inherent in the properties of the molecule. So anthocyanins are detected only as the mass of the compound themselves. So one really important thing to consider when looking at polyphenol chemistry is we know there is variability in the substitution of the ring structures. That can be different hydroxyl substitutions. We also know that this molecule can pick up either sodium or potassium. Now, interestingly, the mass difference between a sodium and a potassium ion adduct is close to the molecular weight of a hydroxyl group. So when we analyze this compound as received with its naturally abundant potassium and sodium ions from nature, we cannot differentiate between a split signal or an addition of a hydroxyl group. So this can become very problematic when we're trying to identify compounds or to characterize them very specifically. We have an approach to be able to deal with this particular complex here, and that is to go through a deionization process using a cation exchange resin and subsequently spike with a cesium salt that affords the proanthocyanidins to be detected as mass plus cesium. Cesium has a molecular weight of 133 atomic mass units. So essentially what we're doing is we're shifting the weight of this complex out 133 mass units away from the mass where sodium and potassium caused a discrepancy with hydroxyl substitutions. And I think this will become more apparent as we actually collect some data here in just a moment and then analyze the data to be able to show the differences between analyzing product before and then after deionization and subsequent spiking with cesium. So now I want to talk a little bit about the workflow that I'm going to demonstrate. And this is really quite simple and straightforward. When we receive a sample, we have to solubilize that, get it into solution. We then deionize that sample with a cation exchange resin. We add our cesium. We mix the sample with the matrix and apply that to a MALDI target. We then acquire the data on the Bruker system in the Flex Control software. That data is then processed in Flex Analysis. And based on this data processing, we can issue a certificate of analysis that characterizes the properties of the incoming product. So now what I'm going to do is I'm going to stop sharing my screen for just a moment. And I'm going to switch over to another webcam that will allow me to demonstrate this process in real time. Okay. So what everybody should be able to see now on their screen is a sample of grapeseed extract. And actually, I have 3 individual samples of grapeseed extract here. You can see one up in this corner, one down over here, and another in this corner. And I present it this way just to demonstrate that even though these are all grapeseed extracts, and they all have been analyzed and demonstrated to have the characteristics that are inherent of grape seed, these products and samples can be received and look very different. They're different ingredients by different manufacturers with different structural properties. So what do we do with this powder once we receive it? We put a small amount, about 50 milligrams, in a centrifuge tube and add a solvent, and this could be water, it could be methanol, or it could be an aqueous organic mixture to solubilize the material. And in this case, we have complete solubility of the grapeseed extract. From there, we will move the grapeseed extract into a smaller vial, just for convenience sake. And we're going to use a strong cation exchange resin embedded pipette tip to deionize and remove the naturally abundant sodium and potassium. And that's really just as simple as taking the sample with the pipette tip with the resin embedded at the tip and just pipetting back and forth in this vial 4, 5, or 6 times. That process has now removed the naturally abundant sodium and potassium from this sample. And we've done something very similar with the matrix. So the matrix we're using is DHB, and so we've also deionized our DHB. So the next step is that we mix the DHB with the deionized sample at a 50-50 ratio. And again, this is all laid out and explained very well in the AOAC first action method, the details. So I'm not going to do the mixing now. This is a pre-mixed ratio of matrix and analytic, but I will demonstrate how this is applied to a target and how simple this can be. So now we have the mixed ratios, and I'm going to take my pipette tip here and very quickly take a very small quantity, 0.5 microliters, and place that on this well in well A1. And as Pierre mentioned, I have 384 different options here. So we can put a lot of samples on these targets, and we can do a lot of high throughput analysis. So I'm just going to lay this down in 3 different wells. And what you're going to see as we're talking here is that the samples are actually drying on the well. I'm going to see if I can bring this up to the camera, but you can see the little wells there, and A1, that sample is already dried. And because it's such a small volume, it evaporates very quickly from the environment. So now what I'm going to do is I'm going to move away from this demonstration and back to a shared screen. And I will show how we're going to acquire the data from the MALDI instrument. Okay. So now I'm going to go into this window, and I hope everybody can see now the flex control environment. If you recall, that same stainless steel target that I just plated is what Pierre had introduced into his system. I'm not going to demonstrate the introduction into the system. I already have another plate in the MALDI, and what you can see here is a template of those 384 wells. Where we plated was well A1, and so we've navigated to that location. And in this window here, we have a camera within the MALDI system that actually is taking a look at that well, and we can navigate within that well just by clicking at different locations. What you see here is the dried matrix analyte that has been deposited on the target, and we have loaded a method here that allows us to accumulate data in the reflectron positive mode. And so what I'm going to do is I'm simply going to hit the start button here, and by hitting start, what happens is the laser starts firing. And as Pierre indicated, our frequency of laser is 1,000, and we're accumulating 500 shots at a time. So very quickly, from start to finish, you can see that little glow occur there. We're accumulating data. That's 500 shots within just a second of time. And as we accumulate data, we see these individual peaks begin to resolve from baseline. We can adjust the laser power, the location, and the different parameters here to allow us to get good signal to noise. So once this data is accumulated, we can move over into the Flex analysis software. And so this is data that I accumulated earlier today, and it is of the same grape seed extract that I just plated on the target. And what we see here is a polymer distribution. Each of these peaks here represents a proanthocyanidin. I'm going to zoom in on this, and you can see that there's between this peak and this peak is a 16 mass unit difference. As we described earlier, this could be sodium adducts, potassium adducts, or a difference of 16 mass units due to a hydroxyl substitution. So I'm going to zoom back out again here. I'm going to just put these labels on just to be able to show everybody that what we're looking at here is a polymer distribution in which we have 288 mass unit differences. That's a difference in degree of polymerization. And we also have compounds that have 152 mass unit differences. That is a gallic acid or a gallyllyl substitution on the proanthocyanidin. These are hallmarks of authentic grapeseed proanthocyanidins. So we know that this has very unique structural characteristics that are similar to what is in a grape seed. The extract is very similar. And when we deionize and add cesium, we're shifting from this purple mass, 133 mass units, to a cesium adduct. And I'm going to now label those. I'm going to make this first one disappear. And again, we see that 288 difference and 152. But what we know now is that if there's a 16 mass unit difference between this position and this position, that can only be due to an extra hydroxyl substitution. So in the case of grape seed extract, we know there is variability in hydroxyl substitutions on the proanthocyanidin ring structure. I'm very quickly going to give just one demonstration of cranberry, in which we see that 16 mass unit difference occurring. Again, 16 mass units and a difference of 288 in degree of polymerization. If we deionize and add cesium, we see that there is only one predominant peak here. Maybe a little bit in this case. Let me see if I can't get a little better example here. Yeah, I think this one might be a little bit better. So in this one, we see in the blue sodium and potassium adducts. In the green is a cesium adduct. So we're reducing the amount of sodium and potassium, and we're substituting with cesium. Again, bringing better resolution to the data set. I'm going to switch back now to the PowerPoint presentation for a quick summary. Okay. So real briefly overviewing, we are seeing that MALDI is a fit-for-purpose analytic that is part of an orthogonal approach to supporting authenticity. We saw an application for characterizing the oligomeric polyphenols in ingredients, and this can also be used in final finished formulas. And I want to acknowledge a lot of the work we've done with ABC, USP, and AOAC to be able to help put together guidance documents on the unique fitness and suitability of MALDI. I'd like to acknowledge my collaborators very quickly here. And then I would like to turn over this presentation to Chris Clark. Chris is an application scientist with Bruker Applied Spectroscopy Division here in Wisconsin. And he will discuss the use of NIR as a rapid method for quickly identifying adulterated food products. And so, Chris, I'm going to turn over the controls to you at this time. Hopefully I can do this. There we go.
Thank you, Chris. Hopefully everyone can hear me and see me just fine. So I am going to talk today a little bit about FTNIR and how that can be used as a complementary technique for something like MALDI in adulterated food detection. So what is NIR spectroscopy? It's a type of absorption spectroscopy that uses light in the near infrared region of the electromagnetic spectrum. The FT stands for Fourier transform, and that's a little bit outside the scope of the discussion for today, but it's the specific technique that Bruker spectrometers use, and it has some distinct advantages over other designs of NIR instruments. So what happens in NIR absorption spectroscopy is a source light is used to irradiate a sample, and some of that light will then be absorbed by that sample according to the unique molecular characteristics of whatever is being measured. The light that is not absorbed will then either be reflected in the case of a solid or transmitted in the case of a liquid to a detector. And it's that remaining light that contains information about the sample being measured. It's a type of vibrational spectroscopy. So the light in the near infrared region activates specific vibrational motions of the molecular bonds in the sample being measured. And this produces an absorbance spectrum, which is just a record of how much light is absorbed by a sample across the NIR region. So NIR has some very specific advantages for a conformity evaluation. One, it's simple to use. It requires very little training or specific technical knowledge. It requires little or no sample prep prior to analysis. With just a handful of confirmed reference or control samples, you can very easily build a method for analysis. And then you can very quickly scan those samples to determine whether it will conform or fail based on the reference method criteria. So a little bit about the workflow, that's also very simple. You would start with a handful of these control or reference samples and analyze them using the instrument. The software would then determine a conformity method based on the established criteria of the spectra themselves. And from there, you could analyze production samples or unknown samples and match them against this conformity method to determine whether they conform or fail, again, based on that established criteria. So here's just a real quick visual of what a conformity method looks like. That red line is the conformity index. So samples below that would be passing samples, again, based on the criteria of the reference spectra. And the samples above that, the blue dots above that, would be samples that failed, so potentially adulterated samples. The specific instrument that I'm going to demonstrate very quickly today is what you see in front of you. It's our Tango spectrometer. It's a very compact design, a very rugged instrument with a very intuitive software display that is very popular and very powerful for applications like food adulteration. So I'm going to bring up the software very quickly. So what I've done here is I have put together a very simple conformity method using non-fat dry milks. Milk powder is a very popular food supplement worldwide. It's also a very heavily adulterated food sample. So this could apply to anything like the cranberry or the grapeseed extracts that Chris was previously talking about. It would be the same type of application. So this is a reflectance spectrometer. The source light originates from an aperture at the top of the instrument. And what I have here is a rotator that I'll put on the instrument. This is my non-fat dry milk sample. And this is a sample that would be known to conform. So you press the play button and you can see behind me, this is our software display. So this is what an operator would be looking at while they make the measurement. So very quickly, you put in the name of the sample, you take the measurement, and it gives you a result. And that result, green is good, it conforms. So this is an acceptable sample based on the reference criteria. So now I've got a sample. This is also a non-fat dry milk powder sample, but I have taken just a small amount of baking soda to mix in and create an artificial adulterant. And we will just give this a new sample name and run it. And you wouldn't necessarily need this type of volume if you have a smaller volume sample. The aperture is quite small. This rotator is actually averaging out inhomogeneities in powders from mixing. But you can see that this sample is red, which means that something about it doesn't conform. So this would be a candidate for sending to a company like CPS for further evaluation with a technique like MALDI to more positively identify the specific contaminant responsible for the failure of the measurement or the failure of the result. And with that, I'll thank you for your time and I will send it back to Pierre.
Thank you, Chris, for that nice presentation. And thank you all for attending. So at this time, we will answer any questions. Just a reminder that each one of you has a questions window somewhere in front of you. So if you have any questions, feel free to type them in, and then we will give them to the right person to answer them. So guys, I have a few questions here. Question number one is, I think this goes to Chris Krueger. It says, can all samples be analyzed as received?
Yeah, very good question. The demonstration today was with a very soluble and very purified selective extract, the grape seed extract. If we receive samples that are less purified, we may take those through another step that I did not demonstrate, which would be a solid phase resin cleanup. So this could be something as simple as a C18 SEP pack that could be used to enrich the constituents. So we work with everything from very fibrous materials like cranberry pumice or blueberry pumice to very selective refined extracts. So yes, additional intermediate cleanup steps can be part of the workflow.
Great, great. Thank you, Chris. Next question, I think this also goes to you, Chris. It says, what other classes of polyphenols could be used as markers of authentication?
So again, our focus today was primarily on proanthocyanidins. We also have methods for the characterization of hydrolyzable tannins. These would be compounds that would be found in fruits like raspberries, pomegranate, strawberries. The anthocyanins, the pigments, are also very easily identified and detected. Flavonols certainly can be detected, flavans. So, you know, the unique properties of MALDI is that if we can ionize it, we can detect it. And so very complex mixtures, we don't need necessarily front end separation. The separation occurs in the time of flight. So if we understand the nature of the botanical source, we can look at the unique polyphenols that can be used as part of that profile.
Great, great. Thank you, Chris. We actually have another one for you. I think this will be a quick one. How do your certificates of analysis look like?
Great question. We really have a hybrid. So there are many times we'll be submitted a sample that may be novel, that may not have a lot of published literature to reference. And so we would produce a more detailed report that would include the mass spectra, the interpretation of the spectra. In certain cases, we apply a deconvolution approach to be able to quantify the relative proportions of A-type to B-type linkages or other substitutions. That is presented both graphically and tablature in a table. So there's a number of different ways that we can work with the clients to present the data. If we're looking at something very simple and routine, like a cranberry as part of the AOAC method, then it's typically a spectra, a mass spectra, the deconvolution, bar chart, and a table of relative proportions.
Right. Thank you, Chris. So we have one for Chris Clark. It says, the FTNIR would analyze powder and dissolved samples. I guess they're asking if you can do both powdery samples and solubilized samples with FTNIR.
Yes, you can. So the example I had here is for solid samples, but we also have a liquid analyzer. So if you were dissolving the samples in a liquid, it would be a transmission measurement. So this would be, regardless of the type of instrument you would use, the idea would be for these to be in a more of a production environment for regular routine analysis.
Right. Thank you, Chris. And it looks like there's one for me here as well. Is MALDI also capable of resolving polymers at much higher masses? Well, higher mass is kind of a relative term. Depends on how high in mass you're looking. Usually we're able to get really good resolution in linear mode for anything below 50,000 to 100,000 Dalton. Whereas in a reflectron mode, the resolution usually just fades out around 25 kilodalton. But anything below that, you're able to see basically, isotopic resolution for each one of the, for polymers, for example, you should be able to identify different series, different additives at low molecular weights, or plasticizers that may be in your sample as well. But yeah. So looks like we still have time for a few more questions. For Dr. Krueger, can the method be used for unknown compounds in herbal extracts?
Yes, so very routinely we are submitted samples that have not previously been characterized. And based on the pattern recognition, so essentially what we're doing, at least in terms of the oligomeric polyphenols, is we're looking for repeated patterns. And so as I demonstrated, we have a repetition of 288 mass units that's indicative of a catechin substitution, 152 mass units indicative of a glycosyl or a gallilyl group. So we're looking for those patterns. And interestingly, what I did not demonstrate today is there's another software package that's available. It's called PolyTools. And that software package is capable of identifying these unique repeating patterns. And so that's the first stage we do, is we identify repeating patterns, and then we interpret what that means in terms of what phytochemical structures could be present. So that can also be applied then in the lower molecular weight range in terms of monomeric units and simpler, smaller molecules. But yes, we do a lot of basic discovery work with the MALDI system as well.
Perfect. Thank you, Chris. Let me see, what else do we have? For Chris as well, Dr. Krueger, is it possible to identify the flavonoids and oxidations? I'm not sure if that's actually a clear enough question. Is that?
Yeah, no, it's a great question, Pierre, because this does take place, and we have seen, for example, in apple, if you subject an apple to a processing, you can see oxidative processes. All you have to do is cut an apple open and leave it on your counter, and you're going to see it turn brown, and those are oxidation. So you can detect and follow those oxidation events, because what's happening is you're having a change most of the time in the nature of a number of hydrogens present. So again, understanding and having a directed reason to be tracing it, yes, you can use MALDI to follow oxidation events and synthesis reactions. So MALDI is really nice for a quick understanding of where you are in a synthetic process.
Good, great. Thank you, Chris. I have another one here that seems to be for both of you guys. It says, can either of these techniques be used for quantitation? For example, amount of anthocyanins per gram. So can either MALDI or FTNIR be used for quantitation?
Sure, I can answer that. So yes, you can, for FTNIR, you can use that for quantification. In fact, that's probably one of the primary uses of FTNIR. It's a secondary measurement, so you can calibrate it to any analytes you want for any specific concentration of components, and build a calibration to then automatically determine the level of constituents you have in a sample.
Right.
Good. And I would just make a comment from the side of MALDI. MALDI is not well suited for quantification on a milligram per gram basis, but there are applications where we can look at relative quantification of identified compounds. So it's semi-quantitative if we understand the behavior of the ions in relation to the other compounds that are present. So again, estimating relative A to B type interflavan linkages is a semi-quantitative but very accurate and precise way of being able to characterize that polymer distribution.
Great. Thank you, Chris. And I think that that is basically the time that we have for the questions. So we'll go ahead and conclude this. I want to thank the presenters, Chris Krueger and Christopher Clark. And also thank you all for your attention. I hope you guys have a wonderful rest of your afternoon.
Thanks, Pierre.
Yeah.
Thank you very much.
All right.